cool.
Amazing.
Great.
Okay. Kaichun,
Yeah, so our next speaker will be Amir Hertz. So maybe Amir, you can try to share your screen while I give you a short introduction. I think you probably can directly share. You don't need the host access.
Yeah.
Cool. So Amir is a PhD student in the Department of Computer Science at Tel Aviv University under the supervision of Professor Daniel Cohen-Orr and Professor Rajay. And he is also a research scientist at Google. So he's working on extending image editing capability using generative models and working on 3D understanding generation and editing. And we'll be hearing from him on towards intuitive 3D generation and modeling. Take it, Amir.
Yeah. Thank you. Thank you for the introduction and thank you for the invitation. Can you hear me and see my screen?
Yes, everything is fine.
Okay, great. Yeah, so I will present today some of my works, my PhD works. So mostly in my PhD, I work on 3D representation, different 3D representation for 3D editing and generation and modeling. So my works includes texture synthesis, and this is the left work, on meshes, and also on point clouds, point generation and registration. And we also develop this work on the right for transfer meshes from one chip to another using coordinate-based, adaptive coordinate-based MLPs. And today I will focus on two recent works. The first one, Spaghetti, which is a generative model for 3D implicit shapes, which also learned about the composition. And the second follow-up work called Sense, which we develop a model to control spaghetti using abstract sketches. And I just want to mention a few of my works at Google are not related, but yeah, so they are into the dark side to the images. But if you have a chance, visit the poster on Tuesday, 4:30. Yeah, so the first work I will talk about is Spaghetti, which is a permutation of the title of our work, editing implicit shape to part-aware generation. So Spaghetti is a 3D generative model that learns unsupervised 3D decomposition over generated implicit shapes. Using this model, you can mix between different shape parts and further edit the generated shape using just simple transformation, local transformation. So how does it work? Our network has three main subnetworks. The first one on the left is the composition, middle one mixing, and the third one on the right is the actual shape, occupancy network shape. So the decomposition decompose the global shape on the left, Z, into distinct part vectors. This is T, such that each part represents a single Gaussian, and the whole collection of parts represent a Gaussian mixture model. And we train this decomposition network over a large number of shapes using the log likelihood loss between points sampled inside the shape and the Gaussian mixture model that each shape outputs. And this is how it looks after we train it over many, many shapes and the corresponding surfaces of those shapes. And next we learn, next we process those parts vectors using the mixing network, which is simply a transformer encoder. And the last part is the occupancy shape, where we where we have a coordinate x in the bottom that attends to the distinct parts, vector parts, and it outputs a label, occupancy label y. And it trains, again, using a supervised sample point inside and outside the shape using binary cross entropy. And important part of our training is that we mask, during the training, randomly mask different parts. And it looks something like this. We have different vectors that correspond with different parts, and we mask part of them, and the output should correspond to the same part that we didn't mask, actually. So in that way, we guarantee the locality of the information that each part vector holds. And during inference, it allows us to mixing between different parts. So the last part, which I will not cover in this talk, is that we apply affine transformation. And in that way, we can apply on both the different parts and the coordinates point. And in that way, we can apply local transformation during inference. So during inference, we omit the composition network, and we can mix between, we start with parts that correspond from a single shape, and we can replace shape parts by replacing the corresponding embedding with part vector from another shapes. And this is the first application. And we can apply transformation like rotating, scaling over different parts. And in that way, we can apply local transformation. And the next work I will talk maybe briefly today. It's a very recent paper we published, SENSE, Sketch-Based Implicit Neural Shape Modeling by first author is Alexander Inger from ETH. So in that work, we focus on learning to encode 2D sketch into the embedding of spaghetti. And the most important aspects of this work is that we want to handle abstract sketches, and we want to preserve the part level control that we have in the pre-trained spaghetti model. So we can control the output shape using only sketches of distinct parts and not always the whole sketch of the complete shape. So there are many existing works that try to do similar thing, but one thing that we saw that shared between all those works is that they can handle only very high quality sketches, as you can see here. They are not really something that an amateur or a quick, and you can do it quickly using only pen. Yeah. So there are two main aspects of this work. One thing is that we create a very diverse data set of sketches using both synthetic rendering and partial rendering, where we render only part of the shape using the spaghetti composition. And in addition, we create a synthetic abstract sketches using a recent work, Clipper-Saw, which can take a photo and can create a very good abstract sketch from it, which is a very cool paper. Yeah, so I won't cover the whole network, but the main parts are that we have image encoder, which is a visual transformer that output visual embedding. And the next part, we have query for each part vector of spaghetti that should both output the embedding of this part and another classification score that represent if this part appear in the sketch. So in that way, we can also handle part like sketches from only distinct parts. And the final network is just give the set of embeddings to the pre-trained generative model and output the shape. And the main application are, of course, sketch to shape, as we can see here. But we can also just start from existing shape and only draw a distinct part and just replace those parts with the existing shape. Or we can start from only some parts of the shape and let the spaghetti model complete it like we saw in the previous work. And that's it. That's my talk. Our code for spaghetti is available, and the code for Sense will be publicly available soon. There is now the paper in archive.